today's objective, essentially, this is a little bit less refined than the first two sessions because we didn't originally plan on doing 3, which is not a problem. But just to be aware, I didn't create like a PowerPoint or anything to go with this one today. Everything's going to be contained in the code. So to get today's workshop started, while I talk a little bit more, if you want to follow along and you have Anaconda installed, you're going to need to make sure that you have the workshop files downloaded and extracted into an unzipped form or a decompressed form. One thing I'll talk about as an introduction to this workshop, the title says like data wrangling, text, and beyond. The truth is we're going to do it in a different order. So we're going to do a little bit of data wrangling at the front end. Those of you that are really familiar with Python or you've really gotten your head around it in these past couple of weeks, this may not be that challenging to you. This will be just me showing off a few more utilities and functions that I think people will find useful from a like data management point of view. Then the second portion is going to be the beyond, which is really just outside of the Jupyter environment. So we're going to talk a little bit about installing new packages or new libraries, like instead of pandas, using other tools. Installing those, getting those to work. Also, I want to demonstrate how some data scientists and data analysts share and display their code, especially code made in a Jupyter environment on GitHub. I just have a couple examples to show you what that looks like. We won't do a GitHub demonstration. That is its own kit of information, but you can follow up with tutorials on your own to learn that. And then, assuming we have time and assuming things are going well, the last section, I'll switch gears and do a little bit on like how to work with text data using both pandas and scikit-learn. So step 1, if you have Anaconda installed, I'm going to launch Jupyter Lab. So real quick, I open my start menu. I type in Anaconda because I want to open the Anaconda prompt. This is a bit of a review from, I guess, 2 weeks ago now. So the Anaconda prompt gives me this pop-up window. And then to launch Jupyter Lab, I'm simply typing Jupyter space lab into the command line of the Anaconda prompt. Okay, so let me get that back up on screen. So I'm launching the Anaconda prompt, and then inside of the command prompt area, typing Jupyter Lab and hitting enter. And like that, I have used the Anaconda prompt, typed in Jupyter Lab, and launched the Jupyter environment. Depending on what you've been doing on your computer, it may be in a different directory. But remember that once you've launched it, you can always go to the little folder icon to start moving your way up the directory. So if I click on that folder, I now have my user directory. And in my case, because I kept all of the workshop files in the downloads folder, I'm just going to open downloads. And then I can see python3.zip, and then I have the extracted form of the folder. And if I open that, that's where you can see the Python code file, as well as a variety of different CSV data files that we will work with today. I'm opening up Python, data, wrangling, the code file, and then this is what my screen will look like. This is what we'll be teaching from. Those of you that are following along, please just give me a quick shout out if you were able to get to this point where you have the code open in front of you on screen. So as I scroll down, part 0, this is the first good test to make sure that the code is working in this cell. So we have import pandas. We've been using pandas as the rock star of working with our data so far. Import pandas as PD. That's going to be just the abbreviation that we use. And now I'm going to import 3 different data sets. This is from the past couple of weeks, we've been working with a data set called youth risk. It's all about the likelihood of getting in a car with a driver impaired by alcohol, some demographic factors that go along with it. So I have arbitrarily chopped this data set up. I've removed some rows. I've made it into a slightly artificially messy data set because that's what data research is like. You often don't get clean data necessarily, or you get disjointed data. So hopefully I've emulated that in a realistic-ish way. And that's what youth risk 1, 2, and 3 represent. They just represent different choppings of the data. So let's explore that. Shift, enter. And this is a good test to make sure, like, did this turn into a number? Did it actually execute the code? And one way we can check real quick, we could do a little plus sign and like, okay, did data 1 actually get imported? Shift, enter, and then like, okay, cool. So now the data is appearing. So now I can trust that, like, yep, the code ran, these CSVs got it to work. If you're having issues like the code isn't executing or you're getting errors, you might just need to close it all down, restart it, relaunch Jupyter. The solution might be different depending on your particular computer. But either way, I've got the data imported, so I'm going to scroll down. This whole section is mostly going to be, part 1 is about combining data sets. I think many of you are probably familiar with SQL. If you're familiar with joins and unions, Pandas has very comparable functions. The two that we're going to focus on is merge, which is like column-wise merging, where you have like a key, and then that key is what you use to match the different data sets together. Or append, which is like concatenation, or it's very similar to union in an SQL context, where you have a data set and you're just appending more rows to the bottom. That's the append function. So those are the ones that we're going to demonstrate and walk through. They're just like really useful utility functions in Pandas. So that's what we're going to go through. Scrolling down, and I've provided links to the official documentation that you can look at on your own. So let me just scroll down to merging by columns, where I have data 1 and data 2. So shift, enter, and we should inspect these real quick to get a quick glance. So in the previous workshops, all of this was one data set. It had all the columns, all the rows. So now, like, data 1 has really just ride and female. Data 2 has grade and age. They both have a shared key for ID. And it's worth noting that those keys are not exactly the same. So we have like 124, 127, whereas here we have like 124, 125, 128. So the rows don't necessarily match up with respect to the ID column. This is something where obviously you are familiar with your own data. You always spend a little bit of time exploring and getting a sense for like how much is missing, how much is there, what's going to happen if I join them together. So in this case, we have mismatched rows, and we don't exactly have the same columns. So let's see if we can merge these together column-wise. Scrolling down, essentially all I'm doing is taking data merge in the same way that I would take data 1, and I would type something like describe, or mean, or standard deviation, something like that. I can run a method function on it. What we're doing is we are basically saying, with data 1, I'll zoom in one step, there we go. With data 1, we want to merge this with data 2. Now, if you're familiar with joins in SQL, you often think in terms of left and right, and it goes in order from left to right. So this is your left data set, this is your right data set, just by default. So if I run this, shift, enter, the result is kind of disappointing, because if I scroll up, data set 2 had 8 rows, data set 1 had 8 rows. Now the rows were mismatched, and so what's it doing here? And the answer is, inside of all of these functions, there are a lot of parameters. This is where you need to use those links, read the documentation to see what the different options are. And I'm just going to like walk through some of the most important ones. In this case, implicitly, it's doing an inner join on all columns. But let's start to make that explicit. That way we can control it as well. So if I scroll down, this example here, data 1 merged with data 2, and then there's a how. How is the method? So this would be like join left, join right, join outer, join inner. By default, the system does inner. So it only looks for rows that are matching, and those are the only candidates for the merge. Anything that is exclusive to one subset of the other is excluded out. Shift enter, and like, okay, so now we've just explicated that option that was otherwise invisible to us. Let's go a little bit further. So data merge, data 2, so that's still the same. But one thing that's worth noting is previously it was merging on all possible columns. Now, data set 1 and data set 2, they only have one shared column called ID, but this is where you can control that. So if you know you have an ID column or what's called a primary key or a foreign key in SQL, on is how you identify that and how you specify that. So on ID is basically saying from data set 1 and 2, this is the column on which the two data sets are going to be joined together. That is the hinge, so to speak. And then outer, let's see what that does as our method. Let me scroll down. On ID, how outer. So before it was inner, so only matching rows. Shift, enter. And how outer, now we see all of the rows appear, and what's happening here is it's populating like logical instances where one data set had a sample observation, but the other data set didn't. The resulting merged data set, it will populate null values for any of those like logically missing entities. Okay, so this would be in SQL either an outer join or a full join or a full outer join, depending on the language you're using. So, and this is probably the most common approach that people want in terms of merging data sets together to get the most robust picture, even if you later then shave down by certain rows or what have you. But just be aware that in order to get merge, to do that fully robust outer join, we have to specify a column and say the method. In this case, it's outer. Now we can also do right and left joins. So if I scroll down a little bit, I've got data 1 merge. Oh, and something I'm going to do here, if I scroll up a little bit, you'll notice that this doesn't necessarily go in order. So like I have 137 here, 136 here. It assembles the merge row-wise with respect to each data set, but it doesn't then resort the information by default. So what I'm going to do from now on, just like any other pandas or Python operation, I've done data merge, and that's all the same, but I'm going to add a new method where I sort values by ID. Shift, enter, and now I get a perfectly sequential 124, 25, 27 list. You'll notice that the index values are wildly out of order because pandas will retain those index labels until you write another function that resets that. We won't do that in this case, but it's just worth noting how that the index labels are independent of these ID values. These ID values which I've arbitrarily created. Scrolling down. So to explore a little bit further, scrolling down past that, data 1 merge, and like we can start to experiment with like data 1 is on the left, and then data 2 is on the right. So again, this makes the most sense if you're already familiar with joins in an SQL context. But in this case, we're saying how left, which is basically saying I want to retain all rows from data 1, no matter what, and then I only want the rows from data 2 that happen to match. So left is the controlling data set. And if I switch this around, if I switch data 1 and data 2 around, that's this next example. So data 2 is now my left, and data 1 is my right. Shift, enter. And if I scroll down a little bit, we can compare these side by side, and we can see like, okay, up here it's 124 and 125 were captured, and here it's 124 and 127. And what I would encourage you to do, if this is like really fresh to you, something that you're not super familiar with, just play around with it. Just mix and match these like two different data 1, data 2, swap them back and forth, because you've already inspected them individually, so you should have an intuition for what they're doing. But you can like take the time to like look at your data in a granular way, look at the other data set, see what you should expect to come out of it, and then play around with changing, is it left, is it right, is it inner, is it outer, and then move these two data sets around and see what comes out of it. So I'm going to keep scrolling down. Now, something that is worth noting, not all data sets are labeled the same way. So you can be even more explicit than what we've done so far. Let's say you have two different data sets where it's like student ID and another data set is, I don't know, ID or ID number or NO. Like it has a totally different label, but the values in those data sets are the keys, like they do match. You can specify like left on a specific ID column from that data set, right on. You could also do multiple, like the data doesn't lend itself to this, by the way, but you can do on equals like, column 1, column 2. So let me just hit enter a couple times. So this example here, those of you that might have very complex data sets and you want to do a composite join, where there isn't just like a clean ID column, it's like ID and name and email address, or some sequence of columns from any given data set that represent a composite key of sorts. You can specify that using brackets and a list using merge. So you can do those composite types of joins. You can also make it very explicit where you're saying, from the left data set, these are my columns. From my right data set, these are my columns. And those are the columns that match for the purposes of joining a data set together. This example is just showing you like exactly the same output that you would get from on, but being a bit more explicit and a bit more expansive. I'm going to keep scrolling down. And as always, in most of my code, I try to provide some useful practice exercise. So we won't pause to do this right now, but see if you can like practice and play around on your own. And if you need a guided prompt, you can use the prompt that I've given you to try and fill in the blanks on your own. Again, pandas like the merge function is all about column-wise joins. The next one that we're going to do is joining by rows or appending rows and appending data, or in SQL language, this might be comparable to unions or insert, kind of depending on how you're using it. I'm going to go ahead and keep going to concatenating by rows. Concat and append are two of the different functions in pandas, so that's why I'm trying to switch to that terminology. But this is literally like, okay, let me run this first line of code after concatenating by rows, which is basically taking data 1, merging it with data 2 on the ID outer, and I'm just gonna do this whole function. By the way, those merges we did before, they don't stick because we never assigned them to an object. So let's assign those to an object, data merged, shift enter, and now I can inspect. Okay, now I have a merged data set. So this has my full outer join. It has data 1 and data 2 slapped together, and like we're ready to go. I have a new data set. So this is where data 3 comes into play, the third data set. Let me scroll down a little bit. And this one is actually notably easier than merge. Data 3, shift enter, like, okay, I've got a data set. It's a lot cleaner too. It doesn't have nearly as many missing values. But here I can see, all right, I've got almost all the same variables. You'll notice that mostly the same variables are there, except now we have a new column that is missing from our original data sets. So data set 1 and 2, even though we merged them to create data merged, those data sets did not contain the variable smoke. But all the other variables match. So ID, female, so we at least have a partial match with respect to the columns that are in each data set, data merged and data 3. So let's see what happens when we try to smash those together. Let me scroll down. Let me zoom back in one step because I think that was requested earlier. So I've got data merge, and again, data merged is the data set. and then dot append. Append is the function, and then inside of it, we have to tell it what is the other. So this is our default data merge, and we are putting something onto the bottom of that data set. That something is going to be data 3. Let's just see what happens. Shift, enter. So it by default went ahead and populated, like it created the smoke column and just went ahead and filled in missing values for all of our data merged. Oh, there we go. So this was data 1 and 2 merged together. It didn't have a smoke column, and then it literally just added a new set of rows from data 3. Now, something that's important to note is that especially if you're adding data 1 by 1, or you're adding data where this index matters. Like, in this case, it's kind of weird because it's got a 0 there and a 0 up here. So that's not the most useful index, to be honest, because there's multiple different indice labels for different rows in the data. Pandas will sometimes allow it for like arbitrary data sets like this. Other times, pandas will get very angry with you and give you an error. And the example where that comes up the most is with time series data and also labels that are not numeric. There's a variety of other edge cases, but the reason I'm mentioning that is it's especially true whenever you just add data that's not necessarily already in a data frame, because data 3 is a pandas data frame object. But what if you just want to add data just in the raw format? This is one of those cases where we need to use a few other options to start overwriting it. So let me scroll down. So if I do data merged append, other 3, so this is the same as before, but now I'm going to pass a new parameter called ignore index equals false. Shift, enter. Now I made it so that this view is scrolling. Right click, enable or disable scrolling outputs depending on which view you want. But this should be the same as before, where the index values are just kind of like all over the place. 0, 1, 9, it's shuffled in a strange way. And if I go down, I can find more zeros, ones. So this is implicitly, this is the default operation of the function. But if I scroll down and I use a different version where ignore index equals true, shift, enter, you'll notice that, here, let me right click, disable scrolling outputs. You'll notice that it basically has reset the index values to just be like, accept whatever the append function produces. So we've got a data set, another data set, append them together, and then reset the index. Ignore the existing index and create a new one. And in this case, creating a new one just starts counting at 0, 1, 2, 3, 4, and we have a new index. This doesn't matter too much when we're merging data sets together necessarily, but what we can do, scroll down, data app is going to equal the outputs there. So data 3, append, other data merge, ignore index, true. So I'm going to create that data set as an object, shift, enter, shift, enter. So now I've got this data. If I scroll down, like, aha, now I have mans. For the data set that didn't have the smoking column, let me right click, enable scrolling output. That way we can see it in a tinier window. So then we see all these values. Okay, cool. We've appended the data set together. You can, and this is something I do in my own data work quite a bit. Often, like if I just need to add one row, I'm not going to go to the work of creating a data frame object just for a single sample. You can add individual samples one by one just as dictionaries. So I'm going to scroll down. I'm going to take data app. So we've appended data 1 and 2 are merged together into data merged. Data merged and data 3 are now appended together. So now that's one data set called data app. So this whole process, we've been jumbling data together. I'm going to append more data. but I'm going to just add one row. To do that, I'm going to other, and then I'm going to pass a dictionary, which is the curly brackets. So inside the curly brackets, you have a sequence of key value pairs. And in this case, that means column label value. So I'll put myself in arbitrarily. I will put in my ID number will be 999. I'm just making that up. Female 0. I am male, so my response to the female variable will be 0. So my value is 0. Driver's license 1. Now this wasn't all of the variables in the data set. If you remember, there's like smoke, age, grade. I have used my squirrely brackets, my curly brackets, to have column, colon, value. So this is my key value pair, comma, and then repeat, comma, repeat. Let's just see what that looks like. Shift, enter. Okay, now if I scroll way, way, way down, so like this is still the same data set. We've told it to ignore the index, so it just resets the index if it needs to. And there we go. The 28th observation is me, 999, female 0, driver's license 1. And because I didn't define any of these other values, any of these other columns, which were what? If we scroll up, smoke, ride, grade, age, because we didn't define any of those values in this dictionary, they're just populated with null values. And what a lot of people will do is like a very common way to approach this from a data analysis point of view. Maybe you're pulling in data, you're looping through other data sets and other rows, and you're getting atomic samples where you just have a sequence of values. This is where you can then write, this is getting a little bit into coding, but with Python, you can write a for loop or a while loop. And for every single one of these samples, you create a dictionary and then you append it to a data set. Create a dictionary, append it to a data set. And it's a rapid way to do a bunch of ad hoc additions or appending individual samples to a data set. Now, to make it a little bit cleaner to read, you could also reformat it. So if I'll make this all kind of difficult to read. So all of this before was on like one line. Here, you don't need to do this necessarily. Just watch what I'm doing on screen. There we go. Okay, so this is what the original line looked like. If you don't remember this from previous weeks, as long as the parentheses are stable, within the parentheses, you can do line breaks to make your code a little bit cleaner and a little bit easier. Same thing goes for curly brackets and a variety of other things. So I'll just hit enter after the parentheses, enter after the curly brackets, enter after every comma, enter before that bracket, enter after this comma, and like so on and so forth. I can reformat it. And this is something nice about Jupyter and most Python editors, is it will auto indent your code in a way that keeps things lined up in a relatively intuitive way. And you can do like arbitrary things. You could hit tab. It is arbitrary. You can put it wherever you want as long as the like parentheses and brackets match. But just be aware, that's what I do in a lot of my code to try and make it a bit tidier. Shift, enter. And then this is the same output that we saw before. Scrolling down, let me just right click, enable scrolling outputs. And then here's another practice exercise. And with these kinds of data sets, especially when you're like just in playground mode, you're not like doing serious work because the data is not being saved and put into a model somewhere. Try to put yourself in the model, or not in the model, in the data set. So like this is a chance for you to practice. Try to append to data app yourself with the key value pairs for each of the variables. It's just a practice exercise, just a way for you to play around and explore. So let's talk about how to like relabel and recode data. Just very quickly, none of this stuff is rocket science. I just want to show you a couple different approaches. So, and by the way, whenever you come to this code, I tried to rewrite this workshop session so that you don't have to start in section 1 and execute the code perfectly in order. You could scroll down to part 2 and just start here, where I will re-import pandas, just for good measure. And I'm going to create a df object that is the youth risk data set. Shift enter, shift enter. This is the data set we were working with over the other weeks of sessions. This should look familiar to a variety of you that have been here before, but you might get data like this, or you might want to relabel the data, maybe because you want to relabel female into a text representation of male, female, or you want to have smoke as yes or no, or Y or N. So let's talk through that. And because anything that I show you today is going from numbers to text, you can always go from text to numbers. So let's do that. Let's scroll down. So one thing I could do, I'm going to create a column from scratch. You'll notice that this doesn't exist up here. Smoke, age, driver's license, this is fixed. I can create variables arbitrarily. So I can say df square brackets, and if this column already exists, I can just create it out of the blue, equals none, a null value, if you will. Shift enter, shift enter. Okay, cool. So now my data set has an extra column, sex underscore loc. And by the way, loc here is in reference to the method I'm going to use for one example of how to recode data. So one example, and we talked about this in the first workshop, was how to subset data, like select the rows and select the columns. So df loc, we select the rows, we select the columns. In this case, I'm selecting df female is equivalent to 1. Shift, enter. So now I have this female 1, 1, 1. I only have that subset of data. If I go further, now this is the most tedious way, but sometimes the most necessary way to recode data. But what I can do is okay, df loc, select my rows, but now I only want to select a specific column. So in this case, it's going to be the sex loc column where there's missing values. Let me scroll down, shift enter, okay, so nones. Now what I could do is repeat that whole process, df loc, select my rows based on a condition, select my column, and assign that a variable. I could overwrite an existing variable, but good data practices, especially in pandas, don't do that. Don't accidentally butcher your original data, is my advice. So with this, we're going to update all of these values with the word female. Shift enter, shift enter. So now I see where female is 1, sex loc is the word female. And then it's still none for everything else because we didn't define male. So let me scroll down. And this is where things get a little bit tedious, but you can create multiple lines where, let's say you had a multinomial category. Instead of just binary 0, 1 encoded data, you have just a bunch of commands in a row, from the data frame, locate these rows in this column, update it to this value, or rinse and repeat. In this case, we only need the 2 because there's only the 2 possible responses, but you could probably imagine how this would work for, let's say you had some survey data and one of the questions was about race and ethnicity, and you had 10 possible responses that were coded as 1, 2, 3, 4, 5 through 10. You could then repeat this process in the same way to individually relabel those things. Shift enter, shift enter. And like that, I've now got females, males, and the values that are still missing, we didn't define what we wanted to replace them with, so they're still missing. They're still none. Now, there's an easier way, especially if you're dealing with categorical or a limited range of discrete values, and that is replace. And this is what you probably saw in my previous workshops, where we can just go down, and instead of doing that tedious location-based approach, we could do df female, take the whole column, and then a function called replace. And then inside of that, and we just talked about key value pairs, the dictionaries, the curly brackets, to replace curly brackets, I want to replace value A with value B. This is my key, this is my value, this is the original, this is the new. Let me just run this command, shift, enter. So this is looking at the original female column, but it's producing values female, female, nan, but then there are still the zeros for the males. Let me scroll down. DF female replace, and I could do 1 colon female. So this is my key value pair. So the word female is matched to the value 1. And by the way, if your data set was reversed, if you had a data set that had males and females listed as strings, you could do the exact opposite of what I'm demonstrating here and switch the strings to a number. So you can just reverse what we've done. And then zeros, males following this comma. Shift enter, and let's use that entire command. So from the data frame using females, replace. What are we replacing? This to replace ones and zeros with female and male. That produced the same set of values that we have here. Assign it to a new column. df sex replace. The replace function. Shift enter, shift enter. And like that, we've used 2 different methods to go through the data set to replace female, which is listed as zeros, ones, or missings, with text strings. Okay? Now, if I scroll down, more practice exercises, more chances for you to see if you can play around with this data coherently. So you could always use the df.loc to like manually select the rows and the columns and then manually update them. But often that's like, 1, it's tedious, it's not always necessary. And in this case, the data is dichotomous. It's zeros or ones, it's binary, it's categorical. It's very easy to replace the values using the replace function. So on your own, this would be a chance for you to practice like, okay, can I replace the ride alcohol driver with a ride replace and fill in the gaps to see if you can generate a new column over here that is basically yes or no's instead of ones or zeros. That's effectively what the practice prompt is meant to do, is just give you like a little bit of guidance on like what you could try out next. So with the replace function, we took known values and replaced them with known labels. Like we knew exactly one-to-one what we wanted to replace things with. Another very common thing is to take a continuous set of variables where we may not know every single unique value, but we do want to cut them up into points. This is called binning or collapsing or categorizing or cutting, depending on what field and tools you're familiar with. So let's do that real quick. Let's inspect the data, df head, like, okay, we've got our data, sex loc, sex replace, we've got that information. Age is going to be the variable we work with now. Age is a continuous variable. It's a pretty small range in this case, but you could imagine another data set where you have a range going from 18 to 80. Odds are age is not a linear predictor of most things you might be interested in. There are like different groups that might have different linear relationships. So you want to cut that up into discrete categories. So how can we do that? 1, we could use the tedious method, df loc, and then we write some conditions where age is less than 15, I want to change the age loc column to lower. And then 15 to 17, middle. And then above 17 is upper. You could do this with df loc as like a really very fixed, very granular control of like this range to this range to this range if you want to. And so let me just run this code, shift enter, shift enter. From that, we can use very granular tools to transform age into a sequence of middle, upper, and lower. Now that's difficult, especially like just for 3 categories. That was a lot of code. And a lot of things could go wrong and a lot of things could get missing. So instead of defining all of this manually, like I've discovered there's a function in pandas called cut. So let's practice that. So I had, in my previous example, we cut up age into lower, middle, and upper, like my 3 age categories. So let's try to do that using pandas.cut. So we're not using a data frame. We're using a function straight out of the pandas module, cut. a vector or an array or a list of data, or in this case, a column of data, dfh4, and it requires that definition of like, this is the data, and then bins. How many binned categories do I want? In this case, I'm just saying 3. So Shift, Enter, and just like that, Pandas has gone through the age column and split it into 3 different intervals that are equally populated. There might be a rounding error. One might have 1 or 2 more than any given other one. But what it tries to do is it tries to find the cut points in the continuous variable of age where an even number of samples are in each of the bins. So this could be useful to get a sense of like quantile points to a certain extent, if that's one way that you want to approach it. But it's a way of just cutting up the data into chunks. Now, this is kind of weird. Like, the data isn't even recorded at this level of precision. It's recorded at, like, ages 14, 15, 16, 17, like pretty discrete variables. We could override this. So instead of saying 3, we could define where our cut points are and then let it do the rest. So let me scroll down. And that's where this next option comes into play. PD cut, age 4, and then I use square brackets. So instead of just a single number for the number of bins I want, I can give it a list. So for bins, I've given it a list where one category is 0 to 14, one category is 14 to 17, another category is 17 to 99. So I do have to define my lower and upper bounds. But if I do that, Shift Enter, I can see more variables, or like a cleaner cut, which might represent some theory that I have, or just a cleaner, tidier way of making my data discrete. Now it's automatically telling us like, okay, it's 14 or higher and up to 17. Rounded brackets means it does not include. Square brackets means it does include the number. Basic algebra range notation. So if I scroll down though, like if you're not really sure, like, is this working? You could feed it an arbitrary data set, PD cut, PD series, range 22. This basically makes an arbitrary list of 0 to 22. Shift Enter. And you can start to see like, okay, how do these labels apply? So the number 14 gets this label, but the number 15 gets this label. The number 18 gets this label. It's a way of spot checking if you need to, like, what are the categorical breakdowns that I'm getting out of this. Now, to be clear, these labels are not friendly to me. I don't like them. They might be useful if you are taking a large continuum and dividing it up into 20 subsets, and you don't have some label that you necessarily want that matters to you for any given category. But in this case, we do have a lower, middle, and upper labeling scheme. So let's use that. So if I scroll down, I can do PD cut, my data set, my bins where I've defined my lower and upper bounds and my cut points in the middle. And then I can, because there are, one way to do this is like how many commas are inside of this square bracket. By defining these cut points, how many bins are you left with? 3. You can feed it a list of labels. And as long as the list of labels has the appropriate number of labels to the appropriate number of bins, Shift Enter, I can now cut my continuous variable age into discrete and labeled categories. Scrolling down, and just like before, all of this we can assign to a new variable, and then we can inspect the data, Shift Enter, Shift Enter. And like that, we have now taken this age variable, and without having to use that really dense, like, df loc these numbers, df loc these numbers, we just said, hey, cut the variables, cut it into these choke points, and give them the appropriate labels. And voila, we have effectively cut or binned or collapsed a continuous variable into a discrete variable. Practice exercise, practice as always. Maybe, like I chose 3 cut points. Maybe you want to split it into 2 or 5 or whatever. Now the age data doesn't go very far, so you won't be able to make it like a 30-point cut. but there is a practice exercise for you to play around with and see if you can make it work on your own. We started this off with like this series. At the beginning, I said download and install Anaconda, mainly because that's my prescribed and preferred starting point for a lot of people, because it comes with Python, it comes with Jupyter, the interface through which I'm using, as well as a bunch of other packages that data scientists and analysts and researchers use extensively, but it doesn't have everything, and you might want to use more tools going forward. So I wanted to spend a few moments talking about, like, okay, what if you discover a new tool? How do you get it installed on your computer? How do you get it up and running? Now, there's a lot of nuance to this. I would encourage you, like, if you really start going down this road, skim some of the links that I've included in the code. I haven't created a PowerPoint with these links. The links are just in the code, so just go through some of them and make sure you understand, in a general sense, like what's working here, how does this work? But for instance, let's say hypothetically something that I know is not included in Anaconda, or at least I'm pretty sure it isn't, is a package called Plotly. Like this is like in the last session we dealt with Seaborn. Seaborn's like a really popular data visualization package, but it's not the only one. Plotly is a free graphing library. I've switched to my web browser now. I was always in the web browser. I switched to that tab. So Plotly is a really cool graphing library. It can make some interactive dashboards using a Python language as its base, as well as R and JavaScript. But like, let's say that I'm just clicking around and I'm going on this journey. I want to use Plotly because Plotly looks nice and cool, or there's a type of graph that, like, I found a really clean example of like a really cool graph or visualization that I want to use and modify to my data. By the way, Plotly is cool. Plotly has some really beautiful graphs, but it's also a little bit weird to get started. So let me just click on scatter plots and, like, hypothetically, let's say I scroll down, like, okay, I really like this visualization. As I hover around, all right, cool. I want to use this. I want to use this in my Python environment. So I go here. I'm just going to copy their sample code. I'm going to go back to Jupyter Lab. And then if I scroll down, like, this is, let me highlight that, like, copy, paste, replace. Like, okay, cool. I'm going to see if I can get their example to work. In this case, I already have Plotly installed, but let me do +, import made up package name as nah. So if I do this, like, this package doesn't exist, okay? It doesn't exist in general. But if I run this line of code, Shift Enter, you might get an error like this. You might also get this error if you run the next line of code for Plotly, because we don't have that installed. Now, if I did pandas as PB, Shift Enter, there's no problem, because we do have pandas installed. It came with Anaconda. But what happens when you want whatever new package you've discovered as in P? If you run that, it doesn't work. So let's install a package. So I'm going to open Anaconda prompt. There's a couple ways to do this. This is the most stable in my experience. Open Anaconda prompt. And what I can do is, and this is where there's links on, but links further up in my code, as well as there's often installation guides on websites for packages. But in essence, if I want to install Plotly, all I need to do in this case is conda install Plotly. And if I type that, and that's very small, by the way, I can't really make it bigger. But if I hit enter, like, what it's going to do is Anaconda, the Conda system, is going to go out to where it knows there's repositories of these packages. It's going to download, try to find the one I've requested, download it, and install it in my environment. Now, in my case, it's going to say, like, hey, oh, wow, look at that. It looks like Plotly is already installed, but it needs to also update some other packages. So when you install a new package, you might get a page like this where it says everything's there, or no package exists. Or if you want to install Plotly, you also need to install all of this other stuff. What do you think? What do you say? Are you okay with that? And then you could say, like right here, yes or no. If I hit yes, it will go through the process of installing Plotly. In this case, it will update. I have one version of Plotly. It wants to replace it with another version. That's where it's very important to, like, okay, go back, go up here, read this documentation to make sure, like, it's very well written in a technical sense to explain, like, what's happening when you install a package. Do you want to update? Do you not? Whatever. In this case, I have already said yes on my computer before, so I'm just going to type no because I don't need to do that right now. But I'm going to exit, and now I can just test import Plotly as PL. Let's see if that works. Shift Enter. Aha! Okay, so now this works. Let me just delete that cell, or actually I'll comment it out. We don't need that. So now, hypothetically, what I should be able to do is run this block of code where it imports Plotly, a specific version of Plotly, and it does all the things that, if I go back to the other tab, hopefully I will see a scatter plot. Let's see if that works. Shift Enter. Run. And now, by the way, I knew this wasn't going to work. And there might even be an attendee here. I have had questions about Plotly lately. But like there's a big empty box. So is this an error or not? And this is where sometimes you have to troubleshoot, like, wait a minute, is there something wrong with my interface? Is there something wrong with Python? Plotly, I'm highlighting Plotly in particular because it is a beautiful visualization software. But sometimes you do need to not use JupyterLab. I like JupyterLab. JupyterLab is very pretty. It keeps things easy and tidy to work with. But it doesn't work with all tools, or not all tools are designed to work with it. So to get this to work, I'm just going to scroll up a little bit. I'm going to switch to Jupyter Notebook, which is a different interface. In this case, in the documentation on the Plotly website says this. So I'm going to switch to Jupyter Notebook, which I could do by like searching for Anaconda and clicking on Jupyter Notebook in the Start menu. But really, all I'm going to do is you could change the URL that is in your browser. So like I've got Plotly here, or not Plotly, I've got my URL where it ends in lab. We're going to replace it to end with tree. Let me close this. I'm just going to click this link. And now it opens this is still Jupyter, by the way, and it will still open Jupyter files like the code that we've been working with. It's just the older, and honestly, older and more stable interface. So let me find my code again. And by the way, I would encourage you to just kind of watch me right now. You don't need to worry about doing this hands-on at the moment. But I'm going to go to Downloads. Maybe. There we go. Downloads, and then navigate into my workshop files. Aha, there we go. Python data, wrangling, and text. Let me click that. So now I see a slightly different view. I'm still using the Jupyter system, but it's a different interface. In this case, it's the Jupyter Notebook interface. Part 4, this was incorporating tools into our Python experience. This was where I opened Anaconda, typed conda install Plotly, explanations here. But if I scroll down, now I can see Plotly works much better in Jupyter Notebook, and it's interactive. I can like zoom in. Oh, by the way, another cool thing of Plotly, like here's the data I want to look at. Click, drag, and it will then zoom in kind of an interactive dashboard way. Plotly is just a super cool package, by the way, so that's why I'm highlighting it. But the idea is we had to install Plotly because it wasn't by default included in Anaconda. And then, like, in order to get Plotly in particular to work, I need to be flexible with which tools I'm using. JupyterLab is what we've done basically this whole workshop series in. But in this case, Plotly is Like it actually displays using the Jupyter Notebook interface better than in Jupyter Lab. Okay, that's the point of all that. And if I go back, let me go to the Scatterplots website. So let's say that I found Plotly. On this web page, there will often be like, hey, here's some descriptive info, here's some sample code. But usually there's also installation guides, because different packages might have different requirements or different expectations or different notes that they offer. So in this case, it always behooves you read the documentation, like make sure that you understand the tools you're using. So in this case, I will click on new to Plotly, and then it's like, okay, it explains what it is, and then, aha, they have a getting started guide. Let me click on that. And now if I scroll through, I can see like, all right, here's how they installed it, or here's how we installed it using Anaconda. And if I keep scrolling through, it explains to you step by step, like what is needed for different components in order for this stuff to work. Plotly is a well-written package. Other packages won't be as well-written, but most of them will have some page or some stage where they explain like how to install and how to most effectively use the tool. Okay, so that's one thing that I wanted to talk about. This is the beyond Python. So we're not like doing any code. It's more like, okay, I discovered a new Python package. How do you install it? You install it by simply opening Anaconda, assuming it's a standard package, conda install, package name goes here. And then from there, once you get it installed, once you get it set up, then you should be able to open your Python code, import the package, and use the package. So with that, another thing that I want to talk about, going beyond, let me close that. Okay, so I'm back to Jupyter Lab. I don't need Jupyter Notebook for the rest of this workshop. So Jupyter Lab, I have my code open. If I scroll down, another thing that I want to point out, you'll see this a lot with data science-y people, but one thing that's very helpful, this code file, this like everything we've been doing with parts 1, 2, and 3, all of this can be uploaded and shared. GitHub is probably the most popular way to do that. And I just want to highlight, I'm not going to talk to you about Git or GitHub. You can do it with point and click. You can make your repositories private. But the point is, like, let's say that you want to share your code, especially with people you don't work with. Like if you want to go to a conference and you want to share what this code looks like, without necessarily sharing your underlying data, GitHub is a tool you might want to explore a little bit just to see, like, does this work for me? So let me click on one of these examples. Georgia Policy Lab. This is my GitHub account. So GitHub is dense. It's mostly used by programmers and developers for sharing code, modifying code, and doing like collaborative software development. But it also works for our purposes as data analysts, researchers, and people who might want to publish our results. So all I've done is I created a repository or a project, and inside of that, I uploaded the code file that we've been working our way through today. If I click on this, and I think I've made this public, so you should be able to view it too. This link up here, this URL, I could share this up here, that URL. I could share that with anyone in the world, and like I've shared it with you, you could go to this link and see like, oh, here's some code. Here's some code. Here's all those annotations. Here's some code and outputs. The idea is that you can show people line by line, like, here's my code, here's my outputs. Here's my code, here's my outputs. And it's a way of making science more reproducible, to be honest. Sharing your results, letting other people see the exact mechanisms you've used to arrive at some analysis. While, and this is important, like, I've imported the data in the code, but if I go back one step, you'll notice that there is no code here. So I haven't had to share my code with anyone. They don't get that underlying data unless I choose to include it in this data, in this GitHub repository. It might be something you want to do. Maybe GitHub is a platform you could consider using for this. NVIDIA, one of the most valuable companies on earth, does like anytime you see something fancy or crazy with machine learning and image recognition, there's probably good odds that NVIDIA hardware is the tool that's driving it. NVIDIA has a research group. Microsoft has a research group. Google has a research group. And they will also use GitHub. Now, they're not using necessarily Python notebooks, but they are using GitHub as a platform by which they share their results, their experimental design, their code structure, and in this case, even their data sets. So if you're not familiar with it and it might be something of interest to you, maybe look into GitHub as like a way of using a platform to share your code and share the work that you're doing. So those are the, like, from the title of this workshop, Data Wrangling, Text, and Beyond. That was the beyond. The beyond is like, okay, how do I get more packages in to use other tools? Also, like, I wanted to show GitHub as a mechanism of like, okay, once I have this notebook ready with my codes and my outputs and it's set up just so I can upload it and share it somewhere for whatever purpose might be appropriate. Before we go into the last section, part 5, working with text data, which is like going back to code, back to like data analysis, are there any questions about any of that stuff? Are there benefits to using Jupyter Notebook over a Jupyter Lab? Ultimately, so like when I switched from Jupyter Lab to Jupyter Notebook, I was choosing like which type of interface I was using. You can think of it as like older and newer versions of Microsoft Word. So some features get lost and work better or worse in older or newer versions. Jupyter Notebook, the interface is just a bit older, but also more stable. So when people are developing Python packages, they often work by default in the Jupyter Notebook interface, whereas Jupyter Lab, it might take, by the way, you can get Plotly to work in Jupyter Lab. It just requires a little bit of configuration. But whether or not that's true for any given tool is very ad hoc. But ultimately, the Jupyter Lab versus Jupyter Notebook interfaces are literally just an interface. This code file here, that's the same no matter what. So once you get your code and your outputs configured, like that is a fixed code file that can be moved to other computers and interfaced with using other tools, uploaded to GitHub. So the file itself doesn't change. It's just like how it gets displayed and interpreted on your web browser. I don't know too many specifics about the difference. To be honest, it's rare that I run into the need to switch from one to the other. But the reason I highlight that is you will sometimes run into that. So it's just good to be flexible and understand, like, read the documentation, read the installation instructions, and just be flexible with which interface you end up using. Let's work with text data. Text data is the thing I love to do the most. What I'm going to show you in this part 5 section of code is not a replacement for like really diving deep into text analytics. There's a lot to learn there. And I might be biased because I do a lot of text analytic type stuff. But I know it's one of those things that people struggle with because Python and R and like these tools lend themselves really well towards like quantitative data analysis, data that's like ones and zeros, continuous variables, or like categorical variables that are pretty well defined. Working with text data is working with something that's unstructured, which can be a challenging jump for some people, especially in a Python environment. But I bet a lot of you have some fun text data to work with. Many of you might have like narratives or case samples, or like when you give a survey, there's like always an option that says like, please explain anything else that you want to say. And you get this free text response. How do you start working with that? Now, the answer to how you start working with that methodologically is wide open. It depends a lot on the data, your objectives, how big your data is. But let's get started with a text sample that I've drawn from Twitter. I actually used the Twitter API to go through. So, like, for instance, here's the Twitter website, and I'm on the DeKalb County Schools official Twitter page. And what I've done is I've created an artificial data set for the DeKalb County Schools, Fulton County Schools, and Atlanta Public Schools. Let me go back to Jupyter Lab if I can figure out how to do that. Let me scroll down. I provided a bunch of links to talk through, like, different things that we're not going to have time for today. Regular expressions. We'll briefly touch on bag of word models. But I mostly want to show you how to start getting unstructured text into a structured form in a fairly simple way that we can lead to, like, word counts, frequency counts. Like, how many times is a word said in a data set? And Twitter is always a nice, fun pile of text. So let's scroll down. Part 5. Import pandas, in case you haven't done that. Tweets is going to be the data set that we use. PD read tweets.csv. Shift, enter, shift, enter. So looking at the data set real quick, we can see, like, okay, I've got the number of favorites, the number of retweets, which Twitter account it came from. There's only 3 options. There's Fulton, DeKalb, and Atlanta. And then what we're really going to be working with is like, okay, what happens when I have this unstructured data, these pieces of text? So, like, how do we start really working with text data? How do we start imposing structure on it? So there's a couple utilities in pandas that are they're a little bit different. Like, they involve multiple steps to arrive at a destination. But let's work through some of them. Let me scroll down. So, for instance, I could, let me hit Alt, Enter, tweets, square brackets, tweet underscore content, Shift, Enter. Okay, this is the original data, all right? This is just the column of the unstructured text information. If I scroll down, I can start doing just like we did describe or mean. We did all of these other methods extended off of columns. In this workshop, we did things like merge, replace. So in this case, we're going to take the data and we're going to start doing string operations. So in pandas, that means .str. And then by itself, .str doesn't do anything. We have to then choose what our string operation is. There's documentation, there's links above in the code. But for one, like, let's just do some simple stuff. Upper, Shift, Enter. So now I've normalized all the text because maybe I want to count up the number of times a word appears, but I don't care about capitalization. I know there might be typos, and I just want to make everything uppercase. Or perhaps, if I go down further, lowercase, where I take the Twitter content string lower, and I lowercase everything. Depending on what you're trying to do, that may not be appropriate. Let me see if I can access them. String.lower. If I hit tab, will it auto pop up like just a variety? Ooh, capitalize is an option. If I scroll down, I can find like, ooh, there's find. That might be useful. Get dummies. That could be interesting. We could create a dummy set from just this column. Is digit, lower, is numeric. So I can do a bunch of operations normalized on my string. Again, read the documents. There's a lot of different functions out there. But I want to show you like a handful that might be useful. So for instance, let's do string replace. If you know there's words that you want to normalize, like, what would it be? Try like teacher and teachers, for instance, or like just like any set of synonyms. You might want to do like a search and replace. So in this case, replace, we define the pattern we're going to look for and the pattern we want to replace it with. I'm going to take the pattern space. So just an empty space. And then I'm going to replace it with the word space. So space, the word space, space. What does that mean? What does that do? Let's run this. Shift, enter. And now you can see where like watch DeKalb schools separated by a space here is now watch the word space and then the rest of the sentence. So you can also, you don't just have to search for a word. You can search for like patterns or strings or empty spaces, punctuation. You could search for like you could try to figure out what is the code for this emoji. Search for all emojis and replace them with just like a text placeholder called emoji. This gets very complicated very fast with regular expressions and pattern matching. But the point is, this is something that you might end up using to normalize your text, especially if you have perhaps you have like a bunch of hashtags at DeKalb schools, but then you also have other texts that say DeKalb schools, not as an at or as a handle, but as two separate strings. This is a case where you could take one of those patterns and replace it with the other. That way the data is consistent across samples. Let me scroll down a little bit further. I could do something where this is going to start going into frequency counts, but I could do tweets string lower, so make everything lowercase, and then I could chain together multiple methods. So I could do lower, then upper, then capitalize, then split, then replace. I could do a bunch of stuff all in a row. So if I do these multiple methods together, it one, took the Twitter data, made it lowercase, and then the resulting data set, it then string split. I didn't define a pattern. There is some default options in here that we haven't talked about yet. But basically what it does is it looks for empty spaces between words in the original data set, and it literally splits them apart into atomic items in a list. And maybe you want to iterate through that list. Maybe there's some type of function or operation. This is also how you could get some counts. You could add all these lists together, get the number of unique terms. You could do a variety of Python operations that way. And I'm going to show you a utility that makes that much easier. Let me scroll down. Shift, enter. So how can we start adding some structure? Like I've shown a bunch of methods for like manipulating the text and doing weird stuff with it. Depending on what you want to do, some of them may or may not be useful, but let's start adding some structure to our data. For instance, one of the functions could be like, let's just look for words and then label all of our tweets with whether or not that word exists. So tweet content string contains the word for, and then case equals false. So capitalization doesn't matter. We're looking for the word for. Shift, enter. And now we just get a bunch of trues and falses. Now, one thing to note is like if I scroll up, I mean, we're only seeing a truncated version of the data. The data does extend further off. But we searched for the word for, and I do want to note that that includes like the for in forget. That includes the for in forum. So if you want to be more precise, then you might need to, in your code, add something like space, space. That way it's explicit that this pattern of for exists on its own. Otherwise, you might get responses like deforestation and forget are all valid responses. Let's go down. I want to show you a way that this can become a bit more useful. So tweet content string contains, you'll notice that I said like super and then this vertical bar. Vertical bar means or. There's links above about how regular expressions work. That's what this refers to. But in this case, it's simply put, I'm looking for the word super, out, or simul. Shift, enter. So now you might be starting to build an intuition like, ooh, I could search for a combination of words like superintendent, outside, simultaneous. Like these are different words. I don't know why these would be together. But from that, I still get a singular true-false column. Now, if we put that to work, maybe I want to make new columns. So tweets, keyword education. And that is tweets, content, string contains the word education. Maybe I want to also have a column keyword teachers. Content, string contains teacher or education. Remember, this vertical bar means or. And then schools, string contains schools. Let me just run this code. Shift, enter, Shift Enter. So now we've taken that original data set that is unstructured, and we have intentionally started to impose structure on it. We can take this unstructured set of text and basically do a search and label. Search the text for a word or a pattern. In this case, maybe education or teacher, educator, or school, and then create an indicator column of falses and truths, which could then feed into a regression model. Maybe you're trying to analyze, like, if a tweet contains this word, like, if this is true and this is true, what are the engagement metrics? In like a hypothetical sense, if you're building a linear model or a regression model, trying to predict like what types of tweets are going to get the most engagement, which might also imply which communication strategies, vocabulary, and words are going to have the most social reach if you have some public message you're working on. Now, this is kind of ad hoc. This is boutique. So this is me saying, like, I know I want to look for this word. I know I want to look for that word, this word, that word, inside of the contains function, and then using all of that to create a structured data set. But often, the beauty and the horror of text data is it's often unstructured, and the patterns themselves may not be so obvious, or you might want to do what's called unsupervised learning to just see, like, what is the data that comes out of my data set as opposed to imposing it. So let's do that. Let's scroll down. What if I want to get frequency counts of every single word? This is where we're going to shift gears. We're going to start using a package called scikit-learn. I briefly mentioned it in the regression analysis section of the last workshop. But scikit-learn has a very powerful set of utilities for, like, okay, you've got a bunch of text. Let's chop it up into a bag of words models, which basically says, like, let's get every individual unique word and count how many times it appears in any individual sample. Let's get all of it. Doesn't matter if it's garbage or not. We're going to count everything. So to do that, we're going to import from scikit-learn a function called CountVectorizer. So CountVectorizer, we're going to specify the model. We're going to then fit the model. So counter will be fit to our tweets data. So let me just run this, Shift Enter. Cool, so that worked just fine. I've got my counter object established. Now I can do counter fit the counter to the data, Shift Enter. Okay, now what happened? So now, let me do this, counter dot tab. Now there's a bunch of components and attributes that are associated with the count vectorizer, as well as more functions that we can use. So one of them, let me do counter. There's a function called get feature names. Shift Enter. This is every single, now we didn't specify a lot of the options. When you read the documentation, you'll see that what count vectorizer does is it takes a string and it splits every single string into components based on spaces and non-alphanumeric characters. So punctuation will also split, like the word don't. D-O-N''T gets split into don and T. And then it eliminates anything that's shorter than 2 characters long. That's just by default. We could override it if we wanted. So we're basically asking, okay, in our strings, what are all of the unique character strings, alphanumerics, that are at least 2 characters long? There's 2 zeros. There's 3 zeros. There's this garbage. There's a lot of stuff. If I scroll way down, I'll eventually get to like words like bear. Beautiful, because somewhere in this data set, somewhere in one of the tweets is at least one of these words. If I scroll down, I can put all of this inside of a length function, Shift Enter. I have 1,000 from, by the way, the data set's less than 300 samples. From 300 samples, I have nearly 2,000 unique tokens, alphanumeric patterns. So the next couple steps, the steps go together, but basically I'm going to transform the data set into a dense data frame. So Shift Enter, Shift Enter. So when I convert it to dints, and the notes explain some of this a bit more clearly, but we get a count vector for every single row and every single keyword. Now what I can do is I can put this into a useful data frame. So I'm going to call it tweet counter, pandas data frame, where the data equals that transformation of the data. My columns equal the feature names. And my index, the index of my data frame, is actually going to be the same as the index for my original tweets. Shift enter, shift enter. And now, whereas before we had the Twitter data, we now have the same rows, so that like for tweet number 4, how many times does this keyword appear? 0 times. How many times does this keyword appear? 0 times. Oh, there's an actual one. This keyword appears once in this sample. Now this is what's called a sparse data set because there's mostly zeros and only a handful of observations. So this is kind of useless, ultimately. Like most of this information probably comes from URLs that have like weird, strange URL formulations that are unique to those individual links. Let's start modifying this function. By the way, I'm going to put all of this together into one block of code now. So if I run this, shift enter, I get the exact same output as before, the number of tweets, the number of tokens, and then the data frame. Let me scroll down a little bit further. I'm going to start adding some parameters now to count vectorizer. So for one, let's say that words that matter, words that are interesting, are words that appear at least twice. So like unique URLs, I don't care about those. Like that doesn't give me a lot of insight to my data. So the minimum document frequency, I'm going to set to 2. So any individual token must appear at least in 2 different tweets, 2 different samples. And then everything else is the same. Let's see what happens. Shift, enter. Now we're down from 1,800 tokens to a third of that. We've shaved out 2/3 of our samples. We still see a few strange alphanumeric patterns. We don't see them all because there's still too much. But we've radically shaved down our data, arguably making it more robust. Let me scroll down a little bit further. This is going somewhere, by the way. We could also get more ruthless. We could say a token must appear in at least 10 documents, but no more than, if I give it a proportion, I'm basically saying no more than 75% of the data. So integers, it's counts. Decimals, decimal numbers, proportions, it's percentages. Shift, enter. So more than 10 documents, but less than 75. Why would I say less than 75%? If you think about it, like words like the, a, and, like overly frequent words, probably don't convey too much meaning. If I scroll down, now we're down to just 88 tokens. So we took 300 samples with nearly 2,000 tokens, and we've shaved that down using rules, arbitrary rules, but still rules to say I want high frequency words, but not words that are too frequent in my data set. Let me scroll down. Another example, what if you want pairs or phrases? For example, you're going to hear n-grams used a lot. Unigrams are individual tokens, so New York and Times. Bigrams would be New York and York Times. A trigram would be New York Times, all as one singular holistic token. So the words don't get split up. It's counted as one item. We could do this to look for phrases now. So let me do minimum 5, maximum 75%, but I only want bigrams. So I only want pairs of tokens that appear in at least 5 documents, but no more than 75% of all documents. Let's see what that looks like. Shift, enter. And now you'll see the phrase and more, the phrase and the phrase universal remote, the phrase we can. So now instead of looking at individual words, we're looking at pairs. We could also look at individuals and pairs and trigrams. You could modify this function in a lot of ways. But now we're down to 69 pairs of words. Scrolling down. Let's take this tweet counter, sum, sort values. Let's just see which ones are the most frequent. Shift, enter. So now we can see like, oh, I love probably DeKalb County Schools, and then a link. Visit a link. Thank you. Like, okay, Fulton County Schools Rising Together, and then a link. Ooh, meal package, meal distribution. Like there are meaningful different phrases. So like in a naive sense, what's something we could do with that? We could take this tweet counter, literally the counts of these bigrams, and what we could do is we could take that with our favorites and our retweets from our original Twitter data set, merge it with our tweet counter on the indexes, how outer, shift enter, and then I have this merged Twitter metrics, favorites, and then all of these bigrams, Twitter metrics dot correlation, shift enter. And now I can get a correlation matrix. This is a very naive text analysis approach. But what is the correlation between different phrases and my metrics? Favorite counts, retweet counts. Now I can organize this a little bit. Let me do Twitter metrics, sort by fave count, shift, enter. So now I can see right away, like, okay, favorites and retweets are pretty tightly correlated. But then I can see like gift card also has a 0.1 correlation with favorite count. Pearson's R correlation, by the way. And all of this started from that pandas data frame where I took my text data, I pumped it through that count vectorizer to create this huge body of counts. I then re-merged it with my original data set using pandas and scikit-learn back and forth. The point is there's tools and utilities for you to take text and apply structure. Hopefully these examples are useful to you. But if nothing else, thank you all. Thank you for being with me on this journey through Python.